Right. So now we are moving to consistency transaction processing concepts. You can see that is the biggest when it comes to time at 12 hours compared to others. Okay. So this is the other big topic we have been doing, but distributed database is the smallest, right? So let's look at the content of introduction to transaction processing, single user systems, multi-user systems, and transactions. Problems in concurrent transaction processing, introduction to concurrency controls in database management system failures, and introduction to data recovery. And then transaction states, acid property of transactions and levels of isolation. Then the schedules, serial schedule, non-serial schedule, conflict serializable schedules, testing for serializability of a schedule, using serializability for concurrency control, view equivalent and view serializability, then transaction support in SQL, consistency in NoSQL, that is separate topic, that is update consistency, read consistency, relaxing consistency, cap theorem, relaxing durability and quorums, version stamps. So that is for NoSQL databases. Okay, so that is a completely different topic. First, we'll do the transaction handling for relational databases. That is up to 5.5. Okay. NoSQL related things we can do separately because it's a completely different topic. Okay. Right. So that is the idea. So we will cover most of the 5.1 to 5.5 today. Right. Right. So what is a transaction? And what is concurrency handling? Right. So transaction is set of activities that must be either success as a whole or fail as a whole. So set of activities that must be success as a whole or fail as a whole. So that means out of those set of activities, we must not see partial success or partial failures. Either nothing is done or everything is done. There's nothing called partly done. Okay, so then we say we have a transaction. And the way to handle the transaction is either fully done, success, or nothing is done. Okay, so that is how the transaction must be handled. So these are some examples. So transactions are not just one operations. So just you are doing an insert, just you are doing update. It's a single task. So that single task is either success or fail. Okay, so therefore there's nothing called partial success in a single task. Say you insert a new record to the database. You delete a record. So those are not transactions. If you want, you can think of it as a transaction, but it's just one task. So therefore, there's nothing called partial success. But there are some business transactions which involve multiple activities, multiple database activities. The very good classical example is doing a money transfer from one account to another account. So then definitely amount must be deducted from one account and the amount must be added to the other account. It can be the same data bank. If it is the same bank, of course, it is the same database. But of course, if it is two different banks, from your bank, if your money is deducted, but the other guy's money is added in the another bank, which is under their control. That is not something we are interested because that is two different systems. What we are interested is transactions involved with the same system or the same database. Same database. So same database transaction handling. So if it is different system transaction handling, those are covered in semester 4, enterprise application development. Transactions that involve cross boundaries, cross systems. Part of the transaction is in system 1, other part is in system 2. Okay. What we are discussing is all those part of the activities are happening to the same database. Okay, same database, not different databases. And at any time, if you have any questions, you need to ask, because this is another very challenging topic. Very challenging topic. Now you can see that unlike in semester 1 and 2, now what you have is small subjects which need serious thinking. It's not quantity, it is the quality. It is the seriousness that is required now. It is not effort, physical effort, remembering this and that. Now your memory is not stress. In semester 1, your memory is stress. Now it is your brain that is getting stress. Memory is relaxed. So that is how it goes. So ultimately, if you can't finish your degree program, it is something wrong with your brain, not your memory, right? Your IQ. Can you understand these concepts? Not can you remember these concepts? Okay. Right. So when you transfer money from one account to the other account, from X account, money must be deducted. From Y account to the Y account, the money must be added. It's a transaction. Either both must be success or nothing must be done. If you have a situation where the money is deducted, but we never add it. So that is a business-wise dispute. Okay. Another classic example is double entry in accounting. So in accounting, we have double entries. Whenever there's a debit, there must be a credit. So if you do the debit, you must do the credit. You can't say just only one of that happened. And of course, there are some activities which involve set of things, right? You have to update the bill or order, reduce items from maybe inventory, maybe you have to do some notifications, logging, everything must be done, no, nothing must be done. Okay, so those are called transactions. And of course, in day-to-day life, in even a very simple systems, we have to face transactions. We have to handle transactions. But in your final year project, usually they don't expect you to handle transactions, but they don't usually look at it. But if you handle transactions, that is definitely a plus point when you go for evaluation, Viva. It shows that you are very serious. Okay. But very rarely students concerned about transaction handling, because that they are not very serious about their final year project. Right. So let's look at the terminology. So every transaction must begin or start. So that is starting of set of related activities. Related activities. Then at the end, your transaction is end. That means all those related activities are now done. If all these related activities are successfully done, we can commit it, or the DBMS can commit it. Commit means everything is success. All the things are done properly. But at any time, things can go wrong. Maybe this is success, but this failed. So now what we have to do is say this is success, say this is also success, this is success, and this is fail. Now it's a partial success, because if this is fail, no point doing this. So then what you have to do is we have to roll back. Roll back means you have to undo previous tasks, sub-activities, because the transaction cannot proceed. So therefore, either all the tasks are success or nothing is done. So that means partially done tasks must be undone in case of rollback. So there are two possibilities. Commit, that is everything is success. Rollback, that means the partially done things are undone. So that means it get into this state again. Either it get back to this state or it get into this state. Okay. So you begin a transaction, end transaction. So transaction can end with the result of commit or with the result of rollback. So what are the possible reasons for rollback? Of course, success is a happy scenario. So sometimes you will find that, or your database will find that, so these are the subtasks for the transaction. Maybe doing this subtask, it found that there's a violation of database rule or business rule. So therefore, you are not supposed to proceed. So then, of course, it has to roll back. That is the possibility of violation of business rule or any other concurrency or the constraint is violated. So you can't proceed. Then it has to be rolled back. There can be some internal error occur. Right? Some sort of internal error. Cannot read the file, database file or something. So then, of course, DBMS is still running. But this particular operation cannot be done. So then again, it has to roll back because the database cannot proceed. And there's another possibility of you try to update a record as part of the sub activity, but that lock key is not released due to some reasons. So then, of course, you can't wait forever. So then what the DBMS does is again it roll back because it can't proceed because it is waiting for a lock. You will better understand what is meant by lock in few minutes. Okay. Right. So those are some reasons. There can be some other reasons as well. Right. So when it comes to transaction handling, there are some additional challenges. What are those additional challenges? So additional challenge is concurrency handling or concurrency access handling. So concurrency handling means multiple transactions accessing the same data. Okay, we'll look at it later. Another additional challenge is recovery management. So remember, while you are in a transaction, a particular task can go wrong and then you have to roll back. That is rollback. That is nothing to do with something wrong with the DVMS, no, or the hardware or whatever. Recovery management is needed. This is not recovery management. That is simply the transaction must be rolled back. Recovery management is needed while the DBMS is in operation and some of the transactions are undergoing. All of a sudden, some failure happens. Maybe hard disk failure, operating system corrupt. So all of a sudden, your DBMS is down. So that can happen. So in that kind of a situation, how can we restore the DBMS? So that is why we take frequent backups. From backups, we have to restore, but we don't take backups every second. Maybe the last backup was 1 minute ago, and in between also things happen. Now, how can we recover to the current situation from that last backup? So that is another additional challenge we have when it comes to handling DBMSs. That is called recovery management, right? So those are all part and parcel of DBMS transaction handling. We have to do the concurrency handling. We have to do the recovery management as part of the transaction handling. Okay, so let's look at a little bit more details about what is meant by concurrency handling. So concurrency means parallel, right? Parallel. So when it comes to a database, hundreds of user sessions can be active at a time, hundreds and thousands of user sessions. Think of a banking system. At a time, thousands of people are doing money transfer. Thousands of people are taking money in their ATM machines, depositing. So all these sessions are happening in the same database. But most of these transactions are independent. For example, I am taking money from my account, you take money from your account. Though it is the same table, we are referring to different records. That is not a concurrency issue. But there can be situations where I try to take money from my account someone is trying to deposit money to my account. So then both transactions involve the same record because ultimately my balance must be updated, right? Same balance. So in that kind of a situation, we have concurrency issue. That happens if both transactions are running at the same time, which is rare but possible. Right? Rare but possible. In that kind of a situation, the transaction handling become more challenging. And we have to handle that also because otherwise either my transaction or the other transaction might get overwritten because those happens at the same time. Okay. So that is another very important aspect when it comes to transaction handling. We have to think about that. We have to handle that. Of course, the DBMS has to handle that. Remember, whatever we are learning today, those things are mainly done by the database, not by us. But we must aware of how the things are happening in the database so that in case of failure or something like that, we know the situation. Right. Right. So that is another challenge DBMS have, not us having, DBMS have, that is concurrency handling. Not every transactions have to think about the concurrency, that is transactions which are having overlapping records or referring to the same data. Okay, so that is where the concurrency handling must be done. And of course, I explain you the recovery management. So in case of a failure, not a failure of a transaction, failure of your DBMS system, so we need a mechanism to recover it back to a, if not original state, recover to a stable state. Okay, so that is called recovery management. So we'll look at recovery management in little bit more details after learning some more theory. Okay. Right. So now let's look at what are the database access operations. So you know that from your semester 2, there are 4 main operations in database that SQL support. That is insert, update, delete, and select. Okay. In SQL terms, we call it insert, select, update, and delete. But in general terms, we say create, retrieve, update, delete, or we call it CRUD operations. CRUD operations. So we create a record, we retrieve record those set of records, we update a record those set of records, or delete record those set of records. So we don't do anything other than those 4. Right? So that is why you have SQL statements or the data DMS, data manipulation. SQL statements are insert, select, update, and delete. But when it comes to file level, because ultimately your database is set of files, that is what we have been discussing in the other topic, right? Indexes and so on. So when it comes to file, we have only 2 operations. That is read, write. So that you are already familiar because we have been doing the other topic, physical in tuning and so on. So it's either read the file or write to the file. So therefore, all these operations are combination of read and write operations. For low-level discussions, it's just read operation, no write operation. No set of read and write operations will make your update, delete, insert, success. Okay, so that is how it works. Right, now let's see what happens when you do a select statement. Say select all from employee. Select from employee where employee ID is 1025. So just we have to read the data from the disk to the memory. Remember, we have to access the relevant data block, right, to the memory, and from memory we can retrieve that particular record. Remember, the smallest unit of access is not a record. In your secondary storage, it is data block. So you get the relevant data block and read it. So therefore, it's just a read operation. Just a read operation. You don't have to write back to the disk. So select is a read operation. Then what about insert? Right. So remember, your data file is in this set of blocks. Now maybe this is our next available data block, or maybe our hashing or indexing technique says the new record must go into this block. So again, how do we do the insert? Then we have to read that particular block to the memory. It's a read operation. Then you write that new record to the block, and then write that block back to the disk. So read the block, add the new record to the memory block in the memory, and that now the block in the memory must be written back to the disk. So therefore, it's a read operation and write operation. So insert is read plus write operation. You read the block, write your record, and write the block back. So read block, write block. It's a read-write operation. So the next one is update. Now you can think, right? So again, we have to read the relevant block, having that record, and then do the update in the memory and write that block back to the disk. So again, it's a read and write. Okay. So then what about a delete? So now you should be able to understand. You read the relevant block having that record that we want to delete. Then we delete that record in the memory in that block and write the block back. So therefore, it's again read and write. So you can see that select is just read operation, but update, delete, insert, all three are read and write operations. Read and write operation. Because when it comes to transaction handling, we will only looking at the read write operations. We don't talk about insert, update, delete, select. We just work at read write level. So therefore, insert is a read write, update is a read write, delete is a read write, select is a read. Okay, select is a read. Right. So at any time, if you have any question, you need to ask. At any time, if anything is not clear, you have to ask. Right? Because you have to collect not doubts, but confidence, right? Confidence. Right. So now let's look at the ACID properties of transaction. ACID properties. So a transaction that preserve ACID properties are valid. And if a transaction cannot preserve any of the ACID property, then we say that transaction is invalid. So the database management system's task is make sure that each and every transaction is done with ACID properties preserved. So what are the ACID properties? It's acronym: atomicity, consistency, isolation, and durability. So these are related properties. These are not just mutually exclusive properties. So one property, when you look at it from another way, we get another property. So sometimes you will feel like both are the same thing. Yes, both are the same things. You look at it in different ways. Okay. So what are these properties? Atomicity, consistency, isolation, durability. So let's take one by one, starting with atomicity. So it's a self-explanatory word, atomicity. Atom means something that we cannot divide it further. Paramaanu. Right. So atomicity property says that transaction is the smallest unit. So if you have a transaction, this is the smallest unit that must be success or fail. It is not the individual task. There can't be a situation where these three tasks were success and these three were fail. No, it is the transaction is success or transaction is false. So the unit of the smallest unit of success or fail is transaction, not individual actions. So that is what atomicity is. So that is the basic idea behind transaction. So every transaction must be success or fail at transaction level, not a smaller level. Okay, because if there's a success and failure at smaller levels, that violate business rules. So the second property says consistency. If your database is business rules wise consistent before a particular transaction, at the end of the transaction also, your database must be that your data of your database must be in a business rules wise consistent level. That means no violation of business rules. So that is why when there are partial activities, we roll back. Because if there are partial activities committed or success, then it may result in inconsistency. So that is one of the idea behind transaction. Okay, so no dispute at the end of a transaction. So third property is isolation. I told you that there can be concurrent transactions. So concurrent means different transactions which refer to same data. So those transactions must execute in isolation. They must feel like there is no such situation. Of course, concurrent transaction can happen, but each transaction must feel, or we have to make sure, the DBMS has to make sure that the transactions are happening like one after the other. But actually they are happening parallelly. But logically, it must be equivalent to a situation where transactions are happening, those relevant transactions that is related to the same data, they must logically executed in a way such that they are actually happening one after the other. Okay, so that is what all about serializability that we will discuss later. So that is called isolation. That means the dirty data must not be exposed to the other concurrent transactions. The undesirable dirty data, right? And finally, durability. At the end of a transaction, your data must be saved or persisted. That is the main reason for having database. Whether it's success or fail, it must be saved. Of course, if it is failed, it must be undone. If it is success or committed, those changes must be reflected in the files. So that even when there's a crash or switch off the computer, database machine, the data must be there in the database when you switch on. So that is what durability is. So that is why we want to save it to a database or file. So those are the four properties: atomicity, consistency, isolation, durability. So it may look very simple, but you have to think really seriously and see the interdependency of these properties as well. Because from this point onwards, our discussion is all about preserving these four properties. Continue your transactions preserving these four properties. That is what DBMS is supposed to do. And remember, I told you in the very first day, when it comes to software, the most complicated software in the world is an operating system. So that is why we have just few operating systems like Linux, Windows, Mac, Android, iOS. Actually, those are the serious operating systems. Just few other operating systems which limited usages. Just, right, you can just count using your hand number of serious operating systems. And the second most complicated software is database. That is why we have, I think, even lesser number of databases than sometimes operating systems, the serious guys. Like we have Oracle, Microsoft SQL. So those are the two big guys. Oracle, Microsoft SQL. So then we have MySQL. Then of course the new guys like MongoDB and so on. So just few serious databases are there. And one of the challenging tasks that these databases have to do is handling transactions. If you take something like Microsoft Access, LibreOffice Base, they are not handling transactions because those are personal databases. Personal database means only one user is using, right? Only one user. That is why we say personal database. Right? For example, even your mobile phone, you have personal databases. Only one user. They are not complicated. But Oracle, Microsoft SQL, right? MySQL, so they all support concurrent transactions. So that is why they are very sophisticated. And they preserve the ACID property. Right. So rest of the stuff, I will be using the older note. So that is not the end of the topic anyway. Now I refer to the your other note. So this is the note available in your Google Classroom, but I will be replacing it with the newer note maybe later. Okay. Right. So now we have discussed these concepts. Right. So now let's move on to the possible problems in concurrency handling. So remember, concurrency handling means parallel transactions happening. Right? Parallel transactions happening which involve same data. Say two transactions happening, but this is working with X data and this is working with Y data. Those are not issues for us. It's like you withdraw money from your account, I withdraw money from my account. So those are not challenging things for database. But two transactions involving the same data, so those are the concurrency issues or possible issues are now there. Right, now let's look at what are those possible issues. We don't say those are all problems, possible problems. So we have to handle all possible problems. Okay. Right. So these are the possible problems. We give them names also. Write issue or the lost update. Write read issue or the dirty read or uncommitted dependency. Read write issue or inconsistent summary or analysis problem. And finally, we have the phantom issue or phantom possible issue. Okay. So above conflicts may occur, but not necessarily. May occur or may leads to issues. Right? So write, read, write. Now you can see that the only exception is read. Read is never going to give you troubles. So that is one transaction read particular data, other transaction also read that particular data. So that is not a problem at all. But if there are two transactions, both transactions try to write the same data, there's a possible issue. If one transaction try to read it and the other transaction try to write it, there's a possible issue. If one transaction read it and one transaction write it, issue, right? Read, write, read, those are two different issues. So phantom issue is a different concept, that is another transaction insert data. Of course, that is also sort of right, but we just take it as a different scenario. Okay. Because you insert a different record. One is reading or writing a record and another record is also inserted to that table. So therefore, we take it separate scenario. Right. So now let's take one by one. Let's look at what is write issue or lost update or write possible issue. So here what happens is we must have two transactions. Remember, for a possible issue, first of all, you must have two transactions. There can't be any issues within same transaction. So you need two transactions. Second thing is, those two transactions must refer to the same data. Same data. The third condition is at least one of the operation must be a write. So that is why read is not a conflict. Right. So it must involve two transactions, two or more. Within same transaction, there can't be possible issues. And those two transactions must refer to the same data, at least one same data. And one of the operation must be a write, at least one of the operation. So then only there's possible conflict. So you can see we have two transactions and assume they are referring to the same data and both are trying to write the same data, same record. So that scenario is called write issue. And the result is possible lost update. Right. So let's take an example. So this is my transaction 1. It read a value and do a change. Okay. And while it is reading the value, the transaction 2 also has read the same value X. Now it has also done a change. Now you can see transaction 1 has reduced N from X. Transaction 2 has added M to the X. But both have now read it, not yet written. Now transaction 1 has written the X. That is updated value is written by X. Sorry, transaction 1. And maybe now it is doing some other thing. Because remember, transaction is set of activities. Now it is it has moved to the second part of the transaction. Second task of the transaction. And while the transaction 1 is doing its task, it has already written the X value. Now transaction 2 write the X value because transaction 2 was already and did some changes. Now only it has written the X value. Now you can see that transaction 1 has written the X value, transaction 2 has written the X value. Assume that the originally X value was 100. So this guy subtract 10. Now this guy has written it as 90. Now this guy also read it, but before this guy has written it. So therefore still X was 100 at that time. Now assume this guy has added 20. Now it is 120. Now this guy has written it as 90. Now this guy has written it as 120. Now whatever this guy has written or the transaction 1 has written, which is 90, has been overwritten by 120. So therefore this 90 is now lost. 90 is lost. Because transaction 2 has updated as 120. And now it is also proceeding. After some times, transaction 1 will be committed, assuming that 90 is written, but actually, once transaction 2 is committed, it is 120 in the database, not 90. Okay? So that is wrong. Because ideally, it should have been 100 minus 10, 90. Then to that 90, you have to add 20, that make it 110. Ultimately, it should have been 110. But now the database says 120 because this is lost. Because before this is written, this transaction has already read the original 100. So that is called write issue or the lost update. It is something that, like, say, when people are pasting posters, so say around 12 o'clock, one person paste a poster. And around 2 a.m. in the morning, another guy has overwritten this. Now, when it comes to morning, this guy's poster is no longer there because it has been overwritten by another poster. So that is same issue here. Same issue. Lost update. Right on the same. If it is this guy is pasting the poster in different board, that is fine. But this is the same board. That is why the first poster is now covered. So same situation is here. So that is called write or the lost update issue. Okay. So if you have any question, you need to ask. Right. So this is the same thing with data. So therefore, the final value is wrong. Final value is wrong. Okay. Right. So now let's move on to the second possible issue. This is called write read issue, or we call it temporary update or dirty read. I think the easiest thing to understand the concept is consider it as dirty read. So dirty means something modified. Modified things is read. So second transaction read something the first transaction has modified, but not yet committed. So then someone will ask, what's wrong with that? Okay. Yeah. So if first transaction and second transaction both success, this is not an issue. Right? The issue is if the first transaction roll back. Why? First transaction did some change to data X. Right. Now, second transaction, read it after modification. That is fine if this is success. After sometimes if it is committed, because then what you have read is correct. But unfortunately, there's a possibility that this transaction roll back. So later this transaction roll back, therefore it is changing this to original value, but you have read the dirty value and you have proceeded with the dirty value. Therefore, your transaction is now wrong. So that is what write read issue is. So that happens only when the first transaction is rolled back, but that possibility is there. If first transaction is also committed, then your transaction is also committed, that is not issue. But there's a possibility of your transaction, first transaction is rolled back, and without knowing that, you commit your transaction. So then your data is wrong. Your results are wrong. Maybe you took a report, that report is wrong. Okay. So there are some possible solutions for this, but yes, this is a possible issue. First of all, let's look at whether it's a possible issue or not. Let's not think about the solutions. Right. So that is write read issue, or write read possible issue, or dirty read possible issue. So this transaction has written something. This is the starting of the transaction. So the second transaction, say assume started here, it has read this dirty value because it has already written, but transaction is not yet committed. Now it is doing some changes and blah, blah, blah. Right? Assuming that this is the correct value, but now after some time, this is rolled back. So therefore, this X value is wrong, but that X value is the one that the second transaction read. So therefore, if this is rolled back, of course, this transaction is okay because it has rolled back, but now this transaction is wrong. If transaction 2 is committed, transaction 2 has done a wrong thing and it has committed. That is what write read or the dirty read issue is. Okay. Right. So if you don't have any issue, we'll move on to the third possible conflict. The third possible conflict is read-write conflict or read-write possible conflict. So why I am saying possible? Because this is not a conflict unless this is rollback. But the possibility of rollback is there. So that is why I am saying this is write-read possible conflict. Right. For example, the first one is also possible conflict because if this transaction is, or if this transaction is rolled back, it is not a conflict. But if both are committed, it is a conflict. Okay. So here, if both are committed, it is not a conflict. But if first one is rolled back, it is a conflict. Okay. Right. So now we move on to read write possible conflict. Okay. Write read. Okay, let me read it. If the first transaction is not committed, then the value is not changed. No. So that is another thing you have to understand. Yeah, that is a good question. Now remember, now first transaction, so let's get back to that. Now remember, first transaction want to write this. So therefore it took the data block related to that record and it read that value and it has written back to the memory block. Now the transaction 2 want to read it. Transaction 2 is not going to read the data block again from the data file because the data block is already in the memory. But remember, this transaction has updated that data in the memory. Now the transaction 2 find that it is already in the memory. So I don't have to take it back. So therefore we read from this. So that is the issue. Right. So now it read that data because it's already in the memory. It read it from the memory block. And in the memory block, it has already updated. So that is why you get the updated value. The updated value. Then it is doing some more calculations. Now this has rollback. Rollback means it modify this value back to the original value in the memory. But already this guy has read the raw updated value and proceed with the transaction. So that is the raw. That is what the issue. Okay, that is the issue. So therefore, you have to think a lot of things. Okay, right. So that is why it is a possible issue because both are reading the same data block in the memory. Okay, and things can even go even more complicated. Right, there's something called flushing and so on. Right, so let's not get into that kind of issues yet. Okay. Right. So the next possible conflict is read-write conflict. So this is different. Earlier, write-read, dirty read. So this is read-write. Okay. Okay. So read-write conflict is the first transaction reads something and then the second transaction write the same thing. So X transaction 1 has read X. Say originally X is 100. After transaction 1 read it, transaction 2 has update X to something else, maybe 100, 200. Right? And then assume that transaction 1 want to again read that value. But by that time, it is not 100, it is 200. So earlier, when you read the value X 100, now when you read the value, it is 200. So that is why we call it unrepeatable reads or inconsistency summary. Right? So when you read the same value twice in the same transaction, you get two different values. Okay. So then if you are a critical thinker, you can ask something like this. Why do you want to read the same value twice? Because you have already read it. Right? So why do you want to read the same value twice? So the answer for that is maybe part of a calculation, you read it. But again, you need that, say you are running in a transaction. So that transaction involves generating two reports. So the first report also for the calculation for the first report also, you need to read the value. To generate the second report also, you need to read the value. Now the first report has been done, but it must happen in one transaction. Otherwise, the reports are conflicting. Now, during the first report generation, the value was 100. During the second report generation, value is 200. So therefore, two reports are not consistent. So that is why we say inconsistent summary or analysis problem. So when we analyze data, your analysis is not consistent because at first part of the analysis. So one analysis it is X, in other analysis the value is Y. So therefore it's not consistent. Or in other words, when you repeat the same data, repeatedly read, you get different values because the other transaction has written. Right? So that is why we say read, write. First you read, then other transaction has written, then you read, you get a different value. So, but majority it is read, write issue. Earlier it is write, read issue or the dirty read issue. But this is read, write issue. Read, write issue. Or unrepeatable read issue. Okay. So transaction 2 read it. Now transaction has one written this value. Now again transaction 2 read it. Now you get a different value. Inconsistent summary. Unrepeatable read. Analysis problem. So that is read, write issue. First you read, then other transaction has written. Or very precisely, you can say read, write, read issue. Okay, but we just say read, write issue. Okay, so the final possible issue is phantom issue. Phantom issue. In phantom issue, it's sort of a read, write. So remember, this is read, write. After you read, some other transaction has written, right? Read, write. This is a special case of read, write, right? So this is a special case of read, write. But this is not actually read, write. Special case similar to read, write. Right? Similar to read, write. But this is not read, write issue. The reason is, first you read, can see, first you read the value. Then the other transaction has written. Okay. And then again you read, and there's an inconsistency. So therefore you can see that it's read, write, read again. So therefore that is why I told you that this is very related to the previous issue of read, write. But the difference is, earlier you read a value, other transaction change that value. And when you read the same value again, you get a different value. But here what you do is, you read set of records. You read set of records. You again read set of records. But this transaction has not changed those records. It has inserted a new record. It has inserted a new record. Therefore, next time when you read the same set of records or the same set of condition, earlier maybe you had 3 records, now you have 4 records because the new insert also get into your result because it's satisfied. So therefore, this is not really read-write issue, but similar to read-write. In read-write issue, the same data is modified by the second transaction. But here it is not the same data is modified. The other transaction has inserted a record which is affecting your the same query when you are doing it again. Because the new record is also part of your result now. So that is called phantom phenomena. Right? Phantom phenomena. So this is affecting mostly when we are doing reports. Right? So your report will be again inconsistent because you have a different number of records. So that is called phantom phenomena. So I hope you can understand all these 4 phenomena or 4 issues: write, 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 read, read, write, phantom, which is sort of a read, write, but it's not the same data, rather new in record. But you can see that here we don't have something called read, read issue because read, read operations are not conflicting at all. You also read, I also read. Okay. That doesn't matter. That doesn't matter. Right. So those are the 4 possible issues. Possible, right? I'm not saying that those are always issues, but there's a possibility of issue. Okay. Possibility of issue. Right. So now we are done with the first part, that is what is transaction, what are acid properties, and what are the possible issues. Right? What are the possible issues? So now we want to discuss what are the concurrency control levels or isolation levels that we can preserve when we proceed with transactions. Okay. So these are the possible situations, possible levels that we can enforce, or we can ask the DBMS to enforce. Okay. Because remember, what we are learning is something DBMS does. We try to understand the theory behind that, the mechanism behind that. This is not something we have to do programmatically or whatever. So that is a good story, right? We don't have to do as software developers, but we must understand how the DBMS is handling this. Otherwise, it's a mystery. It's just like computer system subject. We understand how the fetch, decode, execute work, but it doesn't mean that when we are writing a program, we have to think about the fetch, decode, execute. But when we know the fetch, decode, execute cycle, when we know the registries, how your computer processors process your data, that is important for your confidence. Okay. Right. So these are the possible isolation levels in databases like Oracle, Microsoft SQL, MySQL. Okay. Read uncommitted, read committed, repeatable read, and serializable. So the highest safety is serializable. So that means it guards against all possible issues. Right? For example, if you look at serializable isolation level, no dirty reads, no lost update, no non-repeatable reads, no phantom issues. So that means your database, your transactions will happen without giving you any possible issues. All possible issues are guarded. But if you go for the repeatable read isolation level, so you can set the isolation level in your database or in your transaction. So for example, before starting a transaction, you have to set transaction isolation, say serializable. So that is, so then you say begin transaction and you do your SQL statements. So then you do the commit and then end the transaction. So since you have set it to the serializable at the beginning, before doing your starting the transaction, the database will make sure that it handle all these issues. It will never, your transaction will never face dirty reads, lost updates, non-repeatable reads, and phantoms. Okay. But if you set it not to the serializable, rather repeatable reads, right? Repeatable read. Set transaction isolation level repeatable read. That means dirty reads will not happen, lost updates will not happen, non-repeatable reads will not happen, but phantom is possible. Phantom is still possible. Okay. So if you set it to read committed, dirty reads will not happen, but others are possible. If you set it to read uncommitted, that means all these are possible. So that is sort of a default level. Basically, your DBMS is not handling transaction. Concurrency controls are not handled. All these are possible. So then someone will ask, when we have serializable level, why do you want to settle for anything less? Right? Anything less. So the main reason is, in order to preserve serializable level, your database has to do certain tasks which need more resources and which may make your transaction little bit slower. Okay, little bit slower. So therefore, we have to decide which is our preferred level as developers. It's a compromisation between performance and the expected isolation. Okay. And there are some databases or some database operations, Phantom is very rare, or Phantom we don't care. So then you can say repeatable reads is okay, and so on. Okay. but those decisions are taken by experts in databases, database administrators, and so on. Okay, architects, so they can take the decision. Or most of the time, if you are not too much worried about the performance, we can always safely set it to serialize because no issues are there. But if it results in very poor performance, your database is very slow, so then only we can think of relaxing some of those things as long as they are not going to affect us. So that is how usually we go for the highest level. But there are performance issues also. Sometimes we think about relaxing as long as it doesn't affect us. If it doesn't affect us and still it improve the performance, which we really need, then we just relax it. Otherwise, we just go for the full, uh, the highest isolation level. Or else, if you don't care about your transaction, you can go for the least isolation level, or you can just forget about the transaction handling. That is what the final year students are doing, because they don't care about transaction. Their only objective is finish the project, right? Finish the project. So I'm not criticizing them, but so therefore they don't care about transaction handling. So they just do the card operations without transaction handling. Okay, but in commercial industrial level, as a professionals, we must handle transactions wherever necessary. It's a must. Right? So otherwise, you are in trouble, your team is in trouble, your client is in trouble. Think about a banking application which is not handling transactions, airline reservation system that doesn't handle transactions. So everyone is in trouble. Okay, lot of conflicting situations. Same seat is reserved for 2 clients. Right? All the double entry rules are violated in your bank. So some money is deducted but not credited. So many issues will be there. So therefore, software development is not, the professional, industrial, commercial software development is not a job. That is why we need serious, committed people, professionals. That is why we need engineers. Professional engineers get into those serious development. It's මේක තනකොළ කපනවා පොල් කඩනවා තරම් ලේසි වැඩක් නෙමෙයි. ඒ වගේ සීරියස් නැති අයට කරන්න පුළුවන් වැඩක් නෙමෙයි. අපිට ඒ වගේ සීරියස් අය ඕන එකයි ටීම් එකක්. Okay. Right. Right. So next subtopic is how does your database schedule the concurrent transactions? Again, this is not something we do. This is something the DBMS do, but we must understand the theory behind that. Okay. Right. So we'll look at that after the break. Okay. So we will start at say. Okay, so let's continue. So let's move on to scheduling. So remember that the concurrent activities may happen. Right? Concurrent activities may happen, and there can be possible conflicting situations also. Right? While the concurrent activities are happening, while conflicting situations are there, still your database will try to execute these transactions as efficient as possible. So that is what transaction scheduling is. So what is transaction scheduling? While these concurrent transactions are happening, it try to, or it basically execute these transactions, even having possible conflicting situations, as efficiently as possible, at the same time preventing all those issues. Right? Preventing all those issues. That means it makes sure that no issues are happening, but at the same time, it try to optimize the efficiency. So that is what transaction scheduling is. It is done by the DBMS, where we just learn the theory behind that, how it is done. Okay, how it is done. Right. So first we have to familiar with few terms. The first term is schedule. Right, schedule. So it's just a general term. Schedule is set of activities arranged in time-ordered manner. Right. For example, schedule for a program, schedule for an event. So first this is done, then this is done, and so on. So, but definitely we need a sequence. After this, after that, this, and so on. Okay. Right. So then transaction schedule is set of actions of a transaction arranged in time-ordered manner. If that schedule is for a transaction, we call it a transaction schedule. So the idea is to optimize our schedule, right, while preventing all issues as well. So how do you optimize? You make sure that you preserve the asset properties. At the same time, it is efficient. Preserve asset properties, execute as efficient as possible. Right. So these are the possible transactions, schedules, transaction schedules. What are those possible valid transaction schedules? Remember the word possible valid transaction schedule. That means these are valid, asset properties are preserved, and these are transaction schedules, right? So we can look at two type of transaction schedules, valid transaction schedules, that is serial schedule, serializable schedule. Both are valid. And serializable schedules, we can subdivide it into two subcategories: config serializable schedules, view serializable schedules. So view serializable transaction schedules. First, we will look at serial schedules, which are the easiest to understand, but these are the least efficient schedules. Valid, but not efficient. Serializable schedules are more complicated, and they are valid than more efficient. So therefore, first look at the valid but simple, valid and simple, but not that efficient approach. Right. So serial schedule or serial transaction schedule. It is super easy when you have set of concurrent transactions. That means that they are overlapping. They are overlapping. So what we do in serial transaction schedule is we finish first transaction, then do the second transaction. After the second transaction is finished, only we do the third transaction. After third transaction is done, only we do the fourth transaction, and so on. So then we say it's a serial schedule. It's very simple. If you do transactions one after the other, definitely there are no issues. There are no issues. Only thing is it's not efficient, because other transactions have to wait until the previous ones are done. Okay. But no issue, no conflicts. Okay. Because at a time, only one transaction is handled in the database. Okay. Right. And the other thing is, there are multiple possibilities of serial schedules. For example, say we have three transactions, T1, T2, T3. So there are 2 to the power 3 possibilities. Sorry, not 2 to the power 3, factorial 2, sorry, factorial 3 possibilities. 3 into 2 is 6. Okay, factorial 3 possibilities. Because we have 3 transactions. If you have 4 transactions, factorial 4 possibilities. If you have 2 transactions, factorial 2 or 2 possibilities. For example, if you have 2 transactions, T1 and T2, the 2 possibilities are, remember factorial 2 is 2. That is T1 and then T2. Other possibilities, first do T2 and then do T1. Both are valid. Both are valid. Now, this is something you have to understand. Okay. Now, it's something like this. Say this is a bank. This is a bank. Now, before bank starts, say bank opens at 9, let's assume at 9 a.m. So there are 2 people in front of the bank. Now, the bank, they are waiting for the banks to open. Let's assume there's no ATM or whatever. Now, when the bank opens, they can ask, okay, first you come here, first you come, then the other guy comes. So T1 transaction is done, then T2 is done. Or bank can ask, first you come. Say they are not in a queue. So therefore bank is randomly, the person in the bank is randomly calling first T2 and then his or her transaction is done, then the other transaction is done. Both are valid for the bank. Bank don't care whether it is T1 after T2 or T2 after T1 because both are valid. Right? But it doesn't mean that the result is the same. So this is something you have to understand. The end result may be different. Right? Final state might be different, but bank doesn't care about that. For bank, both are okay. Maybe that is something going to affect these individuals, but it is not going to affect the bank. So for the bank, it doesn't matter whether we do T1 and then T2 or T2 and then T1. That is why we say when we have n transactions, we have factorial n number of possible serial transactions because for the business organization, it doesn't matter. Of course, it will matter for the individuals, but we don't care about the individuals matters. Okay. Right. So can you explain me? This is a question for you guys. I told you for the bank, it doesn't matter whether you do T1 after T2 or T2 after T1. But I told you that it can give you different end results. But both the end results, and now actually doing T1 and then T2 will result state X. First doing T2 and then doing T1 might result in state Y. Most of the time, both these will be the same. T1 after T1 and T2 or T2 or T1, both the results are the end results are the same. But there's a possibility when you do this, the end result is X state. When you do like this, the end result is Y state. So can you give me an example where both the states are the same? Another example, when you do the sequence in different ways, you get different final result. Can you give me example? Assume these two guys have come to do any valid transaction in the bank. Any valid transaction. This is a common sense question, IQ question, and general knowledge question. For bank, it doesn't matter. But the end results might be different and it might affect even these individuals. Actually, they are tasks. Anyone? First, give me example where the end result is the same. Whether you do T1 and T2 or T2 or T1. That is the easier question. So if you have understood what I have discussed so far, you must be able to give me answer for both the questions. If you have really thought about these things in practical level. If not correct answer, at least I expect some sort of answer. I don't mind whether it's correct or not. That means at least you can think about it. I told you these subjects depends on your thinking, logical thinking, right? Not your memory. You can't memorize and pass these subjects. Then, of course, everyone will start developing databases. Everyone will start developing operating systems. Everyone will become Bill Gates, right? No one want even to give a try, at least for the first one. First one means whether it T1 after T2 or T2 after T1, it doesn't affect the end result for the bank or the individuals. retrieving cash from their responsible accounts. Yes, as simple as that. So A has come to withdraw some money from the account. Assume that these are the only two transactions, right? So there are no other transaction happening anywhere in the world related to this bank. I forget to mention that. This is the only branch. Okay, this is the only branch. So then X has come to withdraw money, Y has come to withdraw money. Whether we take the T1 and then T2 or T2 or T1, the result is the same. If both has enough money in their accounts, both will get the money. Assume that the second person hasn't enough money, then anyway, whether you take that transaction first or second, anyway, the result is the same. So we have to say, no, you don't have enough money. But because it is not affected by the other transaction. Right. So that is for scenario 1. Right. So can someone give me a scenario for scenario 2 where the sequence matter for these guys, but it doesn't matter for the bank? Right. These are all scenario 1. I need a scenario 2, that is whether it's T1 T2 or T2 T1 results in two different final outcomes for but the bank don't care about it, but individuals might care about it. So this is the tricky scenario. This is the tricky scenario, but you should be able to think about it. If you have ever visited a bank, right, and if you are a little bit business minded, definitely you should be able to answer this. So I need an answer for the second scenario, where the sequence matter for the individuals, or the sequence results in two different final outcomes. Of course, the bank don't care whether it's first outcome or second outcome, because both are valid for the bank, but it results in two different outcomes. Because without understanding this, no point, or you will never ever understand the idea behind serializable schedules. Right? Config serializability, view serializability. So you will just memorize things without understanding what is happening. What is the idea behind that? Can you give me an example where the sequence matter because sequence results in the end results, but the bank don't care about it? For bank, both are valid. And also the customers also can't say anything about that, because though they may not like it, but they can't blame the bank. Anyone? Now in earlier example, say this guy had 1,000 in the balance, this guy had 2,000, this guy came to withdraw 100, this guy came to withdraw 100. The end result is whether T1 T2 or T2 T1, end result is this guy's account now have 900, this guy's account now have 1,900. Whether we do T1 T2 or T2 T1, the end result is the same. So now I need example where if T1 T2 may be 2x balance, but T2 T1 it gives y balance, which is different balance. Or some other consequence. Okay, so I will give you an example because no one is giving me example. Let's assume that at the beginning, this guy's balance is 1,000, this guy's balance is 2,000. Right? So this guy came to not to withdraw, but to deposit another 1,000 for this guy, because I can go to bank and deposit for another guy, or do a money transfer from this guy to this guy. Say this guy want to transfer 500. Now after T1 is done, if you go by T1 and then T2, After T1 is done, say this guy is transferring money to this guy. So therefore, now A has 500, B has 2,500. Now assume that B came to withdraw 2,200. Now, of course, B can withdraw because already B has 2,500 because this transaction has added 500. So T1 then T2 will make both transactions success because this guy came to withdraw 2,200. Now, if we take other way, T2 and T1, and T2 try to withdraw 2,200, but still it has not received this 500. So therefore, now T2 transaction is failed. But T1 transaction can proceed because this guy is withdrawing, transferring 500 this guy, but by the time the T2 transaction has to be rolled back. So therefore, you can see that two different outcomes. But for bank, it doesn't matter. It doesn't matter. Whether it's T1 after T2 or T2 after T1, bank will say, okay, what we can't do anything for that. Right? We can't do anything for it. For bank, whether T1 after T2 or T2 after T1 doesn't matter. But of course, the final outcome is different. Even the balances are different. Because if you go by T2 and T1, then one of the transaction failed. That is not the issue with the bank, that is the issue with the person. Okay. But both these transactions are valid. T1 after T2 or T2 after T1, both transactions are valid. Because no one can blame the bank. So that is why we say all serial transactions are valid from business point of view. But outcome will be different. Outcome can be different, can be the same, or outcome can be different, but we don't care. So our task is make sure that they are valid. So therefore, all serial transactions are valid, though the outcome can be different. Final outcome can be different. Okay. So therefore, first thing you have to understand is when you have a set of concurrent transactions, n number of transactions, there are factorial n number of serial transactions, possible serial transactions, and all those factorial n number of possible serial transactions are valid, though they can result in different outcomes. Okay. Right. But the only thing is the serial transactions are not efficient because we do one transaction and then you go to the next transaction. It may not be the most efficient. It may take more time for some transactions. Some transactions are waiting long time. Right. So now let's move on to serializable transaction, assuming that you have understood the serial transactions. And serial transactions are always valid, but not efficient. Right. Serializable transaction means a transaction which is equivalent to one of the serial transactions. Right. So what is serializable transaction? This is very interesting topic actually for those who like to think, right? Who like to understand complicated things. It's a very interesting subject. A serializable transaction is a transaction which is equivalent or result equivalent. That means the end result is equivalent to one of the serial transactions. But this is not a serial transaction. This is a non-serial transaction, but it is result equivalent to one of the serial transactions. So then we say our new schedule is serializable schedule. Right? Serializable schedule. Okay. So since every serial transaction is valid, every serializable transaction is also valid. But we can make these serializable transactions more efficient than serial transactions. So that is the idea. So therefore, serial transactions are good. Serializable transaction may be better. Okay, because they are more efficient. Because we are going to mix certain transactions together, but the result is equivalent to one of the serial transactions. So we don't just randomly mix things together. Okay. Right. And identifying a serial or serializable transaction is a hard problem. It's not an easy problem, right? But if someone give you a serializable transaction or say that this is a possible serializable transaction, to check whether it is actually serializable or not, or check whether it is really equivalent to one of the serial transaction is not a hard problem. So finding the serializable transaction is hard. But if someone gives you, check whether it is correct or wrong is not a hard problem. It is a simple problem or relatively simple problem. Okay. Right. So when it comes to serializable schedules, we look at two types of serializability. The config serializability, view serializability. So remember, serial schedules are valid. Serial schedules are valid. And config serializable schedules are also valid. So some of the config serializable schedules are not serial, but they are also valid. So then we have view serializable schedules, they are also valid. But these are all subset. That means serial schedules are subsets of config serializable schedules, and config serializable schedules are subset of view serializable schedule. So therefore, every view serializable schedule is a config serializable schedule. Every config serializable schedule is, every serial schedule is config serializable schedule. Every config serializable schedule is view serializable. But if it is not view serializable, it is non-serializable. That is, it is not equivalent to one of the serial schedules. So those are invalid. So these are the invalid schedules. Right? So these are the invalid because those are not equivalent to one of the serial schedules. But if it is view serializable, that is valid. If it is config serializable, that is valid. If it is serial schedule, of course, that is also valid. Right? That is the idea. So now let's see, check whether a particular schedule is, of course, checking whether a particular schedule is serial schedule is super easy. That is, you just write one transaction after the other in one of any of the factorial in order. Now let's see how to check whether a particular schedule is config serializable and particular schedule is view serializable. Okay. And if you have any questions, you need to ask. Right. So what is mean by conflict serializable schedule? Okay. So config serializable schedule can be made by swapping non-conflicting data access operations. Non-conflicting operations we can swap. So by swapping, we make it non-serial, but still it is conflict serializable. Okay. Because conflict serializable schedules are equivalent to one of the serial schedule. Okay. One of the serial schedule. Now let's see whether a particular transaction schedule is config serializable or not. Okay, config serializable or not. Right. So let's remember, finding a config serializable schedule is relatively hard. But when someone gives you a schedule, to check whether it's really config serializable or not is not that hard. Right. So what we are doing is the easier thing, not the harder thing. Okay. Easier thing. Of course, the harder thing was also in your syllabus when the subject was in semester 5. But now they have taken it to the semester 3. And now you have only the simple part, that is checking the serializability, not making the serializable schedules. Okay, so that is even more interesting. How to make a serializable schedule. But unfortunately, or fortunately for you guys, I don't know. The correct word depends on your attitude. The second part they have removed. Okay. That is making the a serializable schedule. So your task is, when you are given a schedule, check whether is it really conflict serializable or not. Okay. Now remember, what is mean by possible conflict operations? So possible conflict operations comes from different transactions. There's no possibility of conflicting or possible conflicting within the same transaction. Okay. Say transaction 1 is doing a read operation of X. Transaction 1 is again doing a write operation of X. Read and write. Remember, read and write is possible conflict, but because it is done by the same transaction, it is not a conflict. So conflict can happen only cross transactions. So that is the first thing. Second thing is, conflict can happen only when you are referring to the same object, same data. Say this transaction is writing X data, other transaction is writing Y data. No issue, because this is X data, this is Y data. Okay, so therefore, again, if it is same data, you don't have to worry. Sorry, different data, you don't have to worry. If it is same data, only you have to worry. So that means same data, different transactions. Even same data doesn't matter within the same transaction. And the third condition is, one of the operation must be right. At least one of the operation must be right. That means possible issues are with read write, write read, and write write. At least one of the operation must be right. Right. Therefore, read read is not an issue even when you have the same data, two different transactions, but both are reading. That is not issue. So the issue is two different transactions, same data, two different transactions, same data. One is, at least one of the operation is right. That means this is writing, this is writing, this is writing, this is reading, this is reading, this is writing. But this is also reading, this is also reading, it doesn't matter. Though they are two different transactions and same data. So two different transactions, same data, one of the operation is right. That is where the possible conflict is. Possible conflict is. Okay. Because in the exam, sometimes they give you different things and they will ask which of these have possible conflicts. Okay. Right. So let's take an example. So then, of course, there's a way to find whether it's conflict serializable or not. That we will look at later. So that is, we have to draw the precedence graph and see whether there are cycles. If there are cycles, it is not conflict serializable. If there are no cycles, it is conflict serializable. So that we will look at later. Okay. Right. So let's take our first example. So T9 is transferring 100 from one account with balance X to another account with balance Y. Okay. So that is transaction 9. And transaction 10 is increasing balance of the two accounts by 10%. So two transactions. Okay. Right. So let's assume that this is how it is done. This is not a serial schedule. Why? Part of the first transaction happened, then the second transaction has happened, and then the rest of the first transaction has happened. So therefore, this is not a serial transaction. Serial schedule means after the first, the second, or after the second first. For T9 and then T10, because this is T9 and T10, or T10 and T9. So you can clearly see this is not a serial schedule. Okay. This is not a serial schedule. So therefore, straight away you can't say this is valid. Straight away you can't say this is valid, because this is not a serial schedule. Okay. Right. So this is how you do this kind of a question. It's super easy actually. You just remember, we are interested about only read and write operation. So you just write it like set of read and write operation. And remember, first transaction is also working with X data or X record. The T10 is also working with, it's basically working with X data as well as Y data. So this one also working with X data and Y data, because it add 100 to the X and reduce 100 from Y. So this guy make 10% add to the X and 10% add to the Y. So therefore, both transactions are working with both the data. So therefore, there's a possible conflict because you can see these are two transactions. So they involve in same data, right? And one of the operation is write. So this guy is writing, this guy is reading. And of course, this guy is writing also. Therefore, write read is there, write is also there. So same thing is happened to the Y also. This guy is also referring to Y. This guy is also referring to Y. And both guys are writing the Y also. So not just one, both are writing. So two different transactions, same data, one of the operation is right. So that is true for both X and Y. So therefore, this is definitely there's a possibility of conflicting. Right? Our task is check whether is this still valid. Right. So this is how you write it. So this is, we can put it into a much more simple form because we are only interested about the read and write operations. Okay. Right. So now what we do is we make it to a much more simple schedule. So this is my T9, this is my T10. So this is read operation of X. This is read operation of X. So I can write it as read X. And this is not reading or writing, this is a calculation. And this is writing of X. Right. So we just forget about the unnecessary things. We are only interested about read-write operations. And this is read operation of X. So we can say this is transaction 9, read 9x, write 9x, something like that. Okay. So read, this is transaction 10. It is read 10, but the same data. This is calculation. This is write by transaction 10, X data. This is read by transaction 10, Y data. This is write by transaction 10, Y data. Now we are coming back to this transaction. It's a read by transaction 9, Y data. This is a calculation. Write by transaction 9, Y data. Now you can just concentrate on this, which is much more simpler. Okay. Right. So that we have written it like this: read X, write X, then read by, write Y, and in between we have read X, write X, read by, write Y. Read X, write X, read by, write Y. We just write it in this way. It doesn't matter. Okay. Now you can see we can just concentrate on this one now, which is much more simpler. Right. Now what we have to do is we have to draw a precedence graph. Now our task is see whether if you proceed these two transactions, which are not of course serial, and see whether this is okay. And also see whether this is equivalent to one of the serial transaction, one of the serial schedule. Right. So this is how you do it. Right. Easiest way. You have to draw a precedence graph. How to draw a precedence graph? So you take the two transactions, in this case T9 and T10, T9 and T10. If you have three transactions, you draw the third one also. Then see where are the possible conflicts. Okay. Now this is not a conflict because it is within the same transaction. So same transaction, you don't have conflict. Though the same data and one of the operation is right, it is the same transaction. So therefore this is safe. This is not an issue. But what about this? You have read X here, you have write X here. And they are from two different transactions, right? And same data, and one of the operation is right. So therefore, there's a possible conflict here, possible write-read conflict. So that dependence you have to write, it is from T9 to T10 because T9 happened first. So therefore, now we have dependency T9 to T10. Possible conflict going from T9 to T10 because same data, two transactions, one of the operation is right. This is not an issue because same transaction you are doing read and write. This is the first time you are working with Y data, so therefore no issue. This is the same transaction, no issue. Okay, no issues. Up to this point, the only issue is between this dependency. Now you have a read Y. And you can see that you are reading Y, which is written by this guy. Of course, read is not issue, but write read dependency is there. Two different transactions, same data, one of the operation is right. This is not issue because two transactions, same data, but both are read. But these two are conflicting, possible conflicting. And that dependency is going from T9 to T9, T10 to T9. So that means T10 to T9. And of course, this is also a conflict, right and right. But that dependency we have already shown T10 to T9. So therefore, you don't have to show it again. Right? And now you can see there's a cycle. So it T9 to T10 and T10 to T9. It's a cycle. So if you have a cycle in the precedence graph, it is not conflict serializable. Right? So therefore, we can say there's a cycle in the precedence graph. So therefore, this schedule is not equivalent to one of the serial schedule. So therefore, this schedule is not conflict serializable. So therefore, this is invalid. Right. Any questions? Of course, from the very first example, you may not get it. Okay, but maybe after doing another question, you will understand. So therefore, this is not serial. Obviously, this is not serial. And also, this is not conflict serializable because there are cycles. But it doesn't mean that this is invalid. Why? Why? Because now what we said is it is not serial. It is not conflict serializable. That means it is not here. It is not here. But still it might be view serializable. Still we have not checked it. So what we have told is it is not serial. It is not conflict serializable. We are not saying that it is invalid. What we are saying is it is not serial or conflict serializable. Because the question says check whether it is conflict serializable. Okay. Conflict serializable. Right? Because still we have not discussed about view serializability. Right. So this is second example. This is easier because I have given you straight away this diagram. That is what usually happen. Most of the time in the exam, they will straight away give you this one. But sometimes they will give you this one and ask you to first formulate. Of course, that is not a big thing. Right. So this is much easier. Right. So now only thing is you have three transactions. So you have to identify possible conflicting situations and then draw the precedence graph and see whether there are cycles. If cycles are there, it is not conflict serializable. No cycles, it is conflict serializable. Right? So then, of course, we can say to which serial schedule it is equivalent also. But forget about that part. Just do identify the possible conflicting situations and put it into the precedence graph and see whether it's conflict serializable or not. Right? Do it as exercise. Don't look at the answer in the note. Just do it as exercise. I don't mind whether you got it correct or wrong in the first attempt, but just do it. Just do it. And if you want, you can put it into the WhatsApp. I will give you 2 minutes. Okay, right. So let's see. So this is a first operation, second, third, fourth, and so on, right? This is first time you are reading the X, that is not a conflict. And this is the first time the transaction work with Y during this time period. So not a possible conflict. This is again you are reading. So same data, but you are reading, but anyway, you are in the same transaction also, not an issue. Now this is possible issue. Why? So this guy has read it, transaction 1. Now transaction 2 is writing. Same data, 2 different transaction, and one of the operation is right. At least one of the operation is right. So there's a possible conflicting situation. Possible. So that means it is from T1 to T2. Right? Right. So now the W3, the transaction 3 is right in Y. You can see that, of course, transaction 1 has nothing to do with the Y, but transaction 1, 2 has already read Y. So transaction 2 has read Y. Transaction 2 has read Y. And now transaction 3 write Y. 2 different transaction, same data, one of the operation is right, there's a dependency. From here to here, from first one to last one. It is not read write first to next. That is T2 to T3, there's a dependency. Right? So now we have the read one X. First we'll assume that it is so safe. So X, of course, you have read, it doesn't matter. But you can see this guy has written, you are reading. Right? This guy, transaction 2 has written, transaction 1 is reading. But there's no conflict with this one because this one is working with Y, this one is working with X. But this one is working with X, this one is also working with X, and one of the operation is right. So it is first one is this, next one is this. So therefore it is T2 to T1. T2 to T1. Okay. So therefore you can again see that there's a cycle. So T1 to T2, T2 to T1 cycle. So therefore this is not conflict serializable. So this is not going to equivalent to one of the serial schedule. Okay. So not conflict serializable because there's a cycle here. There's a cycle. Right. So do the third one. Now you should be able to do it. Okay. Right. Do the third one. Now this one, it's not in this format. So you have to take it to this format and then proceed. Okay. First take it to this format. We have the following 2 transactions that operates on the balance of 2 bank accounts. The transactions are concurrent. So that means they are happening at the same time. But the assumption is that once the transactions are executed, the balance are the same. That is A equal B. Okay, so don't worry too much about that. Okay, so let me do it by myself because I want to explain few things there. Okay, right. So this is my first schedule or first transaction, not a schedule. This is my first transaction. This is my second transaction. Okay. Now what I want to do is, one of the valid way of executing this is you do T1 and then you do T2. That is, you do these steps. Then at the end, you start doing these steps. Or first you do these steps and then you do the other, the T1 steps. Both are going to be valid. Or, of course, the result will be different, but both are valid. Okay. Right. So this is my first serial schedule. You do the first transaction first, this, and then you do this transaction. Okay. So let's assume initially balance of A is 25. Balance of A is 20, B is also 25. Just assume, right? Or you can say the balance of B is 50. Let's assume both are 25. Now this transaction is done because this is a serial schedule. So we add 100 to A, so therefore it will be 125. We add 100 to B, that is also 125. Now the first transaction is done. Now we are moving to the second transaction because this is a serial schedule. Now the A is multiplied by 2, therefore 125 will be 250. B is multiplied by 2, 250. The final result is both A and B are 250, and this is a valid transaction because this is a serial transaction. ඒක හරියට බැංකුව පටන් ගන්නකොට මේ දෙන්න හිටියා බැංකුව කිව්වා ඔයාගේ වැඩේ කරමු ඔයාගේ වැඩේ වුණාට පස්සේ අනිත් එක්කන්ට වැඩේ කරමු කිව්වා. දෙන්නම ගෙදර ගියා. right? දැන් දෙන්නගෙම තියෙනවා කීයද? 250 250 තියෙනවා. බැංකු පොතේ. Right. So let's assume that we went for the other serial schedule. So that is first we ask T2, then we ask T1. Remember, starting thing is the same. Starting balance is the same, 25, 25. Now we are doing the transaction 2 first. That is, transaction 2 will multiply each balance by 2. So therefore, this balance is 50. This balance is also 50. Now we are doing the transaction 1. We are adding 100. 50 plus 100 is 150. 50 plus 100 is 150. So the final result is, so this is the T2 followed by T1 schedule. This is also valid serial schedule. And the end result is 150 and 150. You can see that if T1 and then T2, the final balance is 250, 250. But if you do T2 and then T1, the final balance is 150, 150. Two different outcomes, but both are valid. Both are valid. So what we care is valid or not. We don't care the outcomes. What we care is valid or not. Both are valid. So those are the two serial schedules. Okay, two serial schedules, two possible serial schedules. Now let's look at another non-serial schedule. Just assume someone has suggested this. Okay. So this is the suggestion. First you do, now remember we want to mix it to make it faster. We don't want one transaction finish and start the second one. So we do the first task from first transaction we do this. Then from second transaction we do this. Then from first transaction we do this. And from second transaction you do this. But make sure, remember that you can't change the order of these activities because first this, then this. First this, then this. You can't change that. That is invalid. Right? But you can mix it. And now let's see what happens. Again, let's assume 25, 25. Adding 100, 125. Here you multiply A by 2. So therefore 125 into 2 is 250. Now you are adding 100 to B. That is 125. Now you multiply it by 2 from the second transaction, 250. So the result is 250 and 250. So earlier, one of the schedule results 150, 150. This is 250, 250. And you can see that the end result is same as schedule 1, serial schedule 1. So this is equivalent to serial schedule 1. Okay. So therefore, there's a possibility of this is valid or conflict serializable schedule because this is the result is or result equivalent to one of the serial schedule. But just because the result are the same, we can't say it is valid. But now definitely we can say that we can't say that this is invalid right now because it is equivalent to one of the result, one of the serial schedule. Now we can double check whether this is really conflict serializable by drawing the precedence graph. Right? Drawing the precedence graph. But before that, let's look at another schedule, schedule C. Okay, schedule C. So there we add 100, then multiply, then second one also multiply, then we add 100 to the B. So that means first step of the transaction 1, then second transaction is fully done, 2 steps, then we again get back to first transaction. That is also not a serial schedule. Now if you start with 25, 25 plus 100 is 125. Now you multiply both by 2. This is 250, this is 50. Now we add 100 to the B, that is 50 into 100 is 150. And the end result is 250 and 150. And you can see that clearly. This is not equivalent to the serial schedule 1 or serial schedule 2 because 250, 150 is not, here it's 150, 150. Here it is 250, 250. So definitely this is not equivalent to one of the serial schedule. So therefore, this is definitely not going to conflict serializable because the result is not equivalent to one of the serial schedules. So therefore, straight away we can say this is not going to work. This is not going to equivalent to one of the serial schedule. But this one is still we can't say 100%, but still we are positive. Still we are positive because it is result is equivalent to one of the serial schedule, but that is not good enough, right? But definitely this is not going to work. Okay. Now let's look at the precedence graph. Precedence graph for this one. Right? Precedence graph for this one. And see whether is it really conflict serializable. Now, if I draw read-write notation, this is read 1x, then write 1x, then read 2, sorry, not x, a, read 1a, first transaction read day, first transaction write day, write 1a. I will draw in the same line or a little bit offline. Read 2a, write 2a, then read 1b, write 1b, read 2b, write 2b. Now we can draw the precedence graph. This is read, this is write, but same transaction. This is write and this is read. So therefore there's a conflicting, possible conflict. Same data, two transaction, one of the operation is write. So that is from 1 to 2. There's a dependency from 1 to 2. And this is also a, that dependence we have already tackled. So therefore you don't have to draw it again. Okay. Now what about this? This is first time we are working with B, therefore no conflict, and this is the same transaction. But now you can see this is B read, this is read, no issue. But this is write, this is read, same data, two transaction. Same data B, two different transaction, one of the activities write. So therefore there's a dependency between, again 1 to 2. Again it is 1 to 2. 1 to 2 we have already shown. Again we have, so you don't have to draw it again. And this is the same dependency because again write is there, but already we have shown 1 to 2. And you can see that only dependency is going from 1 to 2. So there is no cycle. There are no cycles, right? So therefore this is conflict serializable schedule. And yes, it is confirmed because we got the same result also. Right? Same with one. So this result is same as one of the serial schedule. This result is same as one of the serial. But just because your results are the same, you can't say. So you have to draw the precedence graph. Right? So the precedence graph, we can say that yes, it is conflict serializable because no cycles. And you can say to which serial schedule this is conflict serializable also. To which serial schedule? Transaction 1, then transaction 2. This is serializable, conflict serializable to this particular serial schedule. T1 and then T2. See whether 250 is for T1 and T2. This is T2 and T1, right? What we get is 250. Yes, 250 is T1 and T2. First you do T1, then you do T2. So you can see that that schedule gives you the same result as doing T1 and then T2. Of course, this is a serial schedule, but this is not a serial schedule. This is where you can see that we have mixed things, but still this is serializable, conflict serializable to serial schedule T1 and T2. So therefore, this is a conflict serializable schedule, which is efficient than the serial schedule of T1 and T2, but the result is equivalent to that serial schedule. So therefore, this is valid because its result is same as T1 and T2 serial schedule, and it's efficient because we are mixing things together. We are not waiting one transaction to end to start the second transaction. Super important that you understand that, right? And obviously, if you look at the other one, this one, sorry, schedule D, And we know that it is not equivalent to one of the serial schedule, but now let's draw the precedence graph. And it should give us cycles as well, right? So now this is read 1A, write 1A, read 2A, write 2A, read 2B, read 2, that is transaction 2, read B, and transaction 2, write 2B, and again we are coming back, read 1B, write 1B, and let's see what are the possibilities. This is same transaction, and this is write and read, write and read. So that is T1 to T2. And this is again write, we have already shown it. And this is first time B, this is first time same transaction B, no issue. But now you can see this is, you read B here and you write B here, or you write B here, write B here. That is the dependency between T2 and T1. So that is, there's a dependency between T2 and T1. And you can see there's a cycle. Go from T1 to T2, T2 to T1. So that is from precedence graph also, it says this is not valid. And we found that the end result is also not equivalent to one of the serial schedule. But the real decisions comes from not by looking at this. This is just to confirm that. The real way is draw the precedence graph. If it has cycles, it is not conflict serializable. If it doesn't have a cycle, it is conflict serializable to one of the serial schedule. And we can even say what is that serial schedule, right? For example, here we found that it is equivalent to T1 and T2 schedule. So we can find what is the equivalent schedule also. So that is a good news. Okay. Any questions? Or is it perfectly understood? Or if you have any doubts still, I told you, if you are doing IT, computer science, you must 100% understand. Right? If not, we don't teach it. Right? So IT is not for, not like physics, chemistry, right? For biology, where we try to understand the nature. No, this is man-made knowledge. So man-made, you are a man, I am a man. So if they can understand, if I should be able to understand, you should be able to understand. This is man-made knowledge, like maths. Okay. Right. So there are some situations where it's not that easy to tell what is the equivalent serial schedule. But this is very straightforward. We can clearly say the equivalent serial schedule is T1 and then T2. Okay. Right. So now let's do a past paper question, because now we are done with conflict serializability. And you can see we are almost more than halfway to the subject. Right. So let's do a past paper question. Few past paper questions, actually. We don't do anything new. But most of these past paper questions I am taking from final year, because you had only, I think, one paper in the semester 4, because this subject came in last year. Let's look at your paper last year. Let me double check whether I have the paper. That must be 2021. So we have been doing this topic, okay? So we have to just finish that topic. So don't expect that this subject is easy. So the subject is only you can pass if you 100% understand and ask questions, clarify things, right, and so on. Okay, right. So this is transaction. Right? So they have just given you the SQL. Right. So they just ask you whether it's right. So you can do this one first. Right. So just do it. Consider the schedules S with three transactions T1, T2, T3. This is 2021 paper. Note that each RI and WI denotes read and write operations that belong to the transaction TI. Check whether the given schedule is serializable by drawing a precedence graph. Justify your answer. Right, do it. It's not a difficult thing, right? We did similar question. Two similar questions we have done. And not only that, we have identified the reasons, logic, everything. You don't have to do everything. You just have to draw the precedence graph and say whether it's serializable or not. And if it is serializable, you have to say to which serial schedule it is serializable. Right, do it. Take 5 minutes. Or you don't need 5 minutes actually. You can take only 2 minutes. Right. So let's draw it. It's easy, right? So this is transaction 1, transaction 2, transaction 1, transaction 2, transaction 3, transaction 1, transaction 2, right? It's a little bit confusing. I will put it into the way I like it. I like this. Read 1x, read 2x, because this is transaction 2, then read 1y, because then it's very clear. Read 2y, read 3y, read 3y, then write 1x, write 2y. So this is transaction 1, transaction 2, transaction 3. So this is sort of the simplest possible question they can give. Okay. Right. So now we have to find out possible conflicts. So this is read first time, no issue. This is also read. This is also read. Right. So this is also read. This is also read. So read. So far all reads, no issue, right? Read, 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 read. Now this we have write text. Now you have to check, has anyone? Yes, this one has already. So read and write. First read, then write. Two transactions, same data. So that means there's a dependency. T2 to T1. T2 to T1. And this is Y. And then, so then we have write to Y. And this is read 3Y. And read to write. So that is T3 to T2. Right? Two different transactions, same data, one of the operation is right. And see whether there are anything else. So this is write Y, this is read Y. And two different transactions, one of the operation is right. So therefore we have another possibility. That is T1 to T2. So we have T1 to T2 also. Now we have cycle. You can see T2 to T1, T1 to T2. So therefore this is not conflict serializable. So therefore you can't find the current serial schedule also. Right? So you just have to say this is not conflict serializable because there are cyclic dependencies. Okay. Anyone got the answer? Right. So you can see it has not clearly shown it. Definitely there are cycles. Okay. Conflict pairs are there. Right. So you can even write the conflict pair. Usually drawing the dependency graph is okay because you can see there's a cycle. But you can show the conflict pair also because examiner might give you marks for that also. So what is the conflict pair? So this one is this one to this one. Sorry. Okay. So how do you say? This one to this one, this one to this one, and this one to this one. Yes. So T2 to T1, that is this one. Right? T2 to T1, then T1 to T2. This is the conflict. T2 to T1, T1 to T2. So that is where you have the conflict. Not the others, but this is conflicting pairs are there. Okay. So this gives you T1 to T2 dependency. This gives you T2 to T1 dependency. Okay. Read 1y, write 2y. Read 1y, write 2y. Which is that? Right. Read 1y, write 2y. Yes, this is read 1y. So this is read 1. Write 2y. So then read 2x, write 1x. Read 2x, write 1x. හරි ලියලා නැහැ බෑ යා read 3y කියලා ලියලා තියෙනවා. Read 3 වෙන්න බෑ. Read 3 තියෙන මෙතනනේ. So I think this is not properly written. So definitely the conflict is between මේ හරියට print කරලා නැහැ. The conflict is between T1 and T2. So okay, so there's nothing wrong with the T3. So therefore definitely this answer is wrong. So this must be between read 1y and write 2y, read 2x and write 1x. because read 3 has nothing to do with the conflict, right? So therefore, I think they have made a small mistake there. Okay. Right. Right. So this one also you can do. This one also you can do because the same question. Only thing is you have uh, more things there are there. Okay. So do it as exercise, right? Because otherwise, if I do it, you don't get an opportunity to do it. So the C1, C2 are commits. Okay. So at the end, transaction for one is committed. This is transaction 2 is committed. And this is where the transaction 3 is committed. Actually, this is a serial schedule. Transaction 1 read A, transaction 1 write A, transaction 1 read B, transaction 1 read B, then transaction 1 is committed, then transaction 2 read A, transaction 2 write A, transaction 2 read B, transaction 2 write B, then transaction 2 is committed, transaction 3 read B, transaction 3 write B, transaction 3 read P, transaction 3 write P. Actually, transaction 3 is sort of a serial. And actually, that is easier because these are all transaction 1, right? It's serial, right? Serial. This is transaction 2. This is transaction 3. It's a serial schedule. I don't know why they have asked that. Okay, let's read it. Consider the serial. Yes, they say no. Consider schedule S with 3 transaction T1, T2, T3 as follows. Note that RI, WI, and CI denote read, write, and commit operation that belong to transaction TI. Justify it with reason whether the schedule S is serial schedule. So you can clearly see that as pen one set there make a serial schedule here. Because these are all 1, 1, 1, 1, then 2, 2, 2, 2, then 3, 3, 3, 3. Okay. So ඒක නිකන් පොඩි ළමයින්ට දුන්න සීනි බෝලයක් වගේ question එකක් හරි මම දන්නේ ඇයි මේ question එකක් දුන්නේ කියලා හරි පව් කියලා දීලාද කොහෙද right so because you can clearly see this is all our transaction 1 related task then it is committed transaction 2 related task it is committed transaction 3 related task it is committed so therefore obviously මේක අහන්න දෙයක් මම නම් ලියලා ඉන්නේ මේක අහන්න දෙයක්ද කියලා හරි ඔයම ලියලා ඉන්න එපා ඔයගොල්ලෝ paper එකේ so this is obviously a serial schedule okay. So in T1, T2, T3, one transaction starts after the commit of the previous transaction. Yes, right. In each transaction, it completes still all the operations consecutively and start the next transaction. Therefore, it's a serial schedule. So how T1, then T2, then T3. Serial schedule T1, T2, T3. ඒක දුන්නට විරුද්ධව මම නම් කියන්නේ. මොකෝ ලැජ්ජ වෙන්න ඕනේ මේ question එක අහුවෙ ගැන හරි. Right. So we'll take a break. After the break, we'll continue with data structures and algorithms. Right. So let's move on to the data structures and algorithms. So last time we finished tree data structure. And I have uploaded a new node for the tree data structure. Just download it if you haven't taken it yet. Okay. So just take the new node. If you have the old node, new node is much more compact. Okay. So graph, the older node is there. If I have time, I will upload a new node, but we'll be using the older node. Okay. And of course, the UCSC node is also there. Right. So let's move on to graph data structure. Now you should be able to do all the past paper questions. So now we have the graph, then sorting and searching, then syllabus is over. Right. So this is our final data structure, the graph data structure. And of course, this is the most complicated data structure and most versatile data structure because a lot of practical things. It doesn't mean that the stack queues, linked list, trees are not important. Of course, they are very important, but those are more important for problem solving, right? Problem solving. But graph data structure is Very important, because most of the practical scenarios, the real world scenarios, reflects or map into a graph. So graph is set of nodes interconnected. So we have set of nodes. There's no rule or no restrictions. You can just connect it depending on, of course, your requirement. Sorry. So that is what graph is. So it's interconnected nodes. No restrictions. Okay. So therefore, in a way, it's more challenging to model and do operations. But it doesn't mean that it is impossible. There are ways to model it and do it. Okay. Right. So first look at the terminology, and then we'll look at how to model it, and then some operations. Right. So let's move on to the terminology. So this is a graph data structure. So you have the nodes, or sometimes we call it vertex. Okay. So another name for nodes in graph data structure is vertex. Actually, we mostly use the word vertex. Okay. And these are called arcs or edges, because you can have any number of edges or arcs. In linked list, just one edge, if it is single link. In binary tree, just two edges. But here you can have any number of edges, because there's no restriction saying this can be connected to only this much. Okay. And then we have a concept called adjacency. So these two nodes are adjacent nodes. That means those are interconnected by single edge. So I and J are adjacent, J and E adjacent, but clearly B and D are not adjacent. B and C are not adjacent, because B and C are not connected by single edge. Right? Adjacent nodes, or they are not adjacent nodes. Okay. Right. So the next concept is path. So that is self-explanatory. So you start from some place. If you can reach to another place, there can be a path. Something like this path, something like this path, and so on. So those are called paths. So the next thing is degree of a vertex. Remember, vertex is a node, right? Vertex is a node. So degree of a vertex is, or the degree of a node is, number of interconnected nodes. Right? For example, degree of vertex 1 is 2, because there are two interconnections. Degree of vertex 2 is 3, because we have 1, 2, 3. And similarly, degree of vertex 5 is 0, because it is not connected to any other node. Right? So degree of a vertex. So then we have a concept called loop. Remember, precedence graph is also what? Precedence graph is also a graph. And there we check whether there are loops. Okay. Now you can see these subjects are interconnected also. Right. So loop is, if you can start with a node and come back to the same node, then we say we have a loop. If that possibility is not there, then there's no loop. So clearly there's a loop here, right? But this is not a loop, because you can't. There's another loop here. You start from C, you go to A, you come to B, again you come to C. There are two loops here. Okay. So that is called loop. Then order and size of a graph. Order of a graph is number of vertices or number of nodes. The size of a graph is number of edges. So order and size can be different. For example, so you may have 3 nodes, but maybe 4 nodes, but you can see how many edges are there. 1, 2, 3, 4, maybe 5, 6, and so on. So therefore, order and size can be different. Okay. Right. So now we look at the categorization of graphs. So there are two types of graphs, that is directed graph and undirected or non-directed graph. Okay. So directed graph, we have the direction in the node edges. Okay, the direction is there, but in undirected graph, there are no direction. Oh, it's sort of bidirectional. We can go from here to here as well as here to here. But if it is directed graph, from here you can go there, but not from this path, you can't come back. So basically, undirected means something like no, bidirectional. Oh, either direction doesn't matter, or it's bidirectional. Okay. Right, so that is self-explanatory. Right. So then we have connected graph versus non-connected graph. So it's again, you can just look at it and see. So connected graph means from one node, right? There's a path to another node, every other node. But here you can see from here you can go there, but from here you can't go there. But overall, it's a graph. Okay. So that means it is non-connected graph. Okay. Right. So then we have a concept called simple graph. So simple graph is a graph having no self loops and multi-edges. If your graph has no self loop means from a node, you are coming back to the same node. That means there's an edge. So this is not self loop. This is for two different edges, nodes. But if you have something like this, from there, you are coming back to the same. So that is a self loop. Multi-edge means between two nodes, you have more than one path between two adjacent nodes. You can go like this way or that way. So then we say we have multi-edge. So if your graph has no self loops, no multi-edges, then we call it simple graph. Simple graph. So then someone will ask, why can we have multi-edges? Yeah, maybe this is one way of going from X to Y. This is another way of going from X to Y. Maybe this is Colombo and say goal. Maybe you go by the highway, you go by the normal route or by train. Maybe different cost, different time, but okay, something like that. So that is multi-edge. Maybe having different reasons, different context. But if no multi-edges and no self loops, we say it's a simple graph. So then you have the multi-graph. Okay. So multi-graph means the parallel edges are possible. And of course, self loops are possible. Okay. Sometimes we call it a pseudo-graph. It's not really a graph, right? But it's sort of a graph. Okay. Right. So then you can have weighted graphs. Now, so far when we draw graphs, we never add a value for these edges. Right? We just say there's a connection. That's it. But sometimes there can be a meaning for this edge. Maybe that is distance from A to B or cost from A to B. Right? Something like that. Or the amount of rewards you get when you go from A to B. So likewise, if you have meaning, numeric meaning for that edge, we say that it's a weighted graph. And most of the time, what we have to work with are weighted graphs. Okay. If you don't have such a thing, that means you just model that there's a connection between A to B, nothing else. So then it's not a weighted graph. Okay. Right. So then we have directed cyclic graph versus directed acyclic. Acyclic means not cyclic. So directed means it must be first directed graph, not undirected. Okay. So as the word says, you can identify this is directed graph, but it has cycles. If you have directed graph, but it doesn't have a cycle, we say directed acyclic graph. Okay. So this one is directed graph and it has cycles. This is directed cyclic graph. And of course, if this is sort of a schedule, you draw it for the dependency of schedules, this is not conflict serializable. Okay. This is again directed graph, but you can see that there are no cycles. So if you go just there, you struck there. If you start from here, you come here, you go there, you struck there. You start from here, you go there, or go there, go there. Right? So there's no single cycle. No single cycle here. So therefore, this is anyway directed, but a cyclic graph. Directed a cyclic graph. So this is directed cyclic graph. And of course, this is undirected, a cyclic graph. So the next concept is complete graph. So complete graph is a very special graph where if you take each node, it is directly connected using single edge, it is connected to each other node. You can see this is connected to this using single node, to this using single node, to this using single node, and to this using single. And it is true for each and every node. So then we say it's a complete graph. Right? For example, this is a complete graph. And this is a complete graph. So this is a complete graph. Of course, this is not a complete graph, but now it is a complete graph, and so on. Okay. Complete graph. Okay, so each vertex has an edge connecting to all others. Just single edge connecting to all others. Right. So then we have a regular graph. So regular graph means every edge, every node having the same degree. Right. So all these are complete graphs. All these, regular graphs. For example, this one's degree is 2 edges. Everywhere you can see degrees 2, 2, 2, 2, 2. Here, this one's degree is 3. This one degree is 3. This one's degree is 3, 3, 3, 3. It's a regular graph. And you will see that each of these graphs are regular graphs. Right? So these are easy questions if you get a question like that, okay? So look at this, degree is 3. Look at this, degree is 3. Look at this, degree is 3. Degree is 3, degree is 3, degree is 3, degree is 3. It's a regular graph. Okay. Only thing is you have to remember those things as well, right? Regular graph, complete graph, a cyclic, directional, a cyclic graph, directional, cyclic graph. So many different words are there, okay? Weighted graph, multi-graph, simple graph, connected graph, okay? Right. Right. So then we have finite graph versus infinite graph. So that is super simple to understand. So finite graph means you have finite number of nodes and of course finite number of edges. Infinite graph means infinite number of nodes and edges are there. Right. For example, you have decided to visit all the stars in the universe. First you go to this star, then you go to the next star, and it is infinite graph because we don't know even the end of the universe. So it will be an infinite graph at least for our understanding. But if you decided to visit all the places in Sri Lanka, the major towns, so that will be a finite graph. Okay. Right. So then we have few more words. These are not super important, but they have been mentioned here and there. Like path is you start from one place and ends to another place. So there can be multiple paths also, right? For example, you can go like this. Of course, if it is non-directed or bi-directed, you can go like this. So those are called paths. A path is called simple path where you don't repeat any vertex or you don't repeat any edge while you travel. So then it's a simple path. Right? It's a simple path. Right? For example, you start from here, then go there, then go there, then go there. It's a simple path because you never repeated any edge or any node, right? So look at ABFH. ABFH, it's a simple part. Then ABFH, EBAD, right? ABH, right? You can look at it, okay? So those are simple parts, right? So then, of course, you have the walk and trails. You can read it, okay? So trail means no edge is repeated, right? Right. So then we have, I think we discussed the strongly connected graphs, right? Yeah, strongly connected we discussed, right? Regular graph, complete graph. No, we didn't discuss, right? Right. Okay, let's look at the strongly connected graph as well. This is regular graph, right? So we have something known as connected graph, weakly connected graph, strongly connected graph, and not connected graph. Okay. So what is strongly connected graph? From one point or one node, there's a path to any other node. So then we say strongly connected graph. Okay. For example, if I start from A, I can go to D. Okay. From A to D and I can come back to B also. And from A to D to B and B to C. That from A I can go to B, I can go to D, I can go to C. And if I start from D, there must be some path to go to A, like go to B and come back to A. Of course, you can go to B. And of course, you can come to C because you can go to B and come back to C. So likewise, from any node, if you can go to any other node, that must be true for all the nodes. We say that it's a strongly connected graph. Right? Strongly connected graph. So similarly, we have weakly connected graph. So that means it is not strongly connected graph. It's a unidirectional graph which is not strongly connected. But if you ignore the direction, it is connected. So then we say it's a weakly connected graph. Okay, so that means if you look at the direction, it's not strongly connected. But if you forget the direction, now it is connected. So then we say it's a weakly connected. Okay, weakly connected. Right, so then connected component means those components are, it's not a full graph, but those subcomponents are connected. Right? For example, this is not a connected graph as a whole because from here you can't come here. But this component is connected, this component is connected, and this component is connected. So therefore, it's not a connected graph, but we have connected components. We have three connected components here. Okay. Right. So the next concept is articulation or cut point or separation vertex or cut vertices, or the more formal word is articulation point. So articulation point of a graph is a point or vertex where if you remove that vertex, your graph become disconnected. So your graph become two components. So those type of vertices are called cut points or articulation points. For example, if you remove this, for this edge and this edge is also removed, now it is two separate components, two separate graphs. So therefore, this is a cut point. But it doesn't happen if you remove this one. If you remove this one, obviously what happens? If you remove this one, of course, this edge is not there, this edge is not there, this edge is not there. Still, this is a graph, one graph. So therefore, this is not a cut point. Right? So only cut point here are, so this is a cut point, this is a cut point, this is a cut point, this is a cut point. Why? Then this get isolated. So all the other parts are one, but this guy isolated. So therefore, it's also cut point. This is a cut point because then it break it into these things and these three. So likewise, you can see this is a cut point, 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 and this is also cut point because then it isolate everything into this and the other three. But the single color things are not cut points. If you have two or more colors, those are cut points. Those are cut points or articulation points. Right. So then we have bi-connected graph. So let's finish the terminology first, okay? So bi-connected graph is a graph with no articulation point. Now remember this one has so many articulation points. So therefore it is not a bi-connected graph. But there can be a graph where there are no articulation points or cut points. So not a single cut point. So then we say it's a bi-connected graph. Right? Bi-connected graph. So then someone will ask, why are we interested about these things? Especially when it comes to war. Cut points are super important. Right? Because the movement, say these are some military camps. Right? So these are some military camps. So if the enemies manage to, right, if enemies manage to overcome a particular cut point or something like this, all of a sudden now they are separated. So this is isolated from this part. So therefore these are strategically important when it comes to war. Right? When it comes to war, these are strategically important points. If you have something like a bridge here, if this bridge is destroyed, now they are separated. The supplies and everything is separated. So strategically important points. Okay. Of course, there is one usage. And when there's a disaster or something like that, these are critical points because it isolates different areas. Okay. But if it is not a cut point, we have the alternative paths. Right. So bi-connected graph means you don't have such cut points in that graph. Okay. That is good in that kind of situation, less risky. So all these are bi-connected graph. There's no single cut point. Okay. Right. Strongly connected components we discuss. Right. So the next thing is how to model the graph. Modeling a graph. Now the way we model linked list and also the way we model binary tree or the tree is somewhat same. So we have node class and we have the data component, right? Say object type data. Then single linked list, we have another node. In double linked list, we have two nodes. In binary trees also, we have two nodes. So therefore, whether it's single linked list or double linked list or binary trees, we can go for this kind of arrangement because we know how many nodes are there. How many nodes a particular node is referring to. It's predefined. But when it comes to graph, we don't know how many nodes a particular node is connected to. Sometimes it can be 5. For another node, it can be 3. Another node, it can be 2. Another node, it can be 1. And so on. So therefore, we can't model like this. Of course, we can model like this, but that is not going to be very efficient or very general because the number of nodes vary from one node to the other. So therefore, we don't use that approach. Of course, we can use that approach and model it, but that is not going to be a very general approach. So therefore, when modeling graphs, we use a different approach, a more general approach. And before moving to that, so there are so many usages of these graphs, right? For example, networks are graphs. The internet is a graph. Our road network is a graph. Railway network is a graph. If you have the water transmission, water supply, it's a graph. Power supply grid is a graph. Electricity grid. Okay, so you can see telecommunication grids are graphs. So you can see a lot of practical things are graphs. Okay, but they can be connected to multiple nodes. So therefore, what we need is a general approach, because we don't know exactly how many graphs are there, how many nodes are connected. So this is how you model it. Again, we model the vertex, that is a node, as a class, but we don't refer to other nodes. Or vertex does not refer to other vertices. It just keep the data. Okay, let's say char or object or whatever. Okay. If it is just we are keeping a label, we can just say char, or you can just keep object. Okay. And nothing else. This is just a constructor. So therefore, vertex is another name for node. Is very simple, just keeping the data. Now our challenge is how to model these edges. Right? How to model these edges. So what we do is in graphs, we model these edges in a separate way, because there can be so many possibilities. And sometimes even multiple edges are also there. So therefore we model edges separately. So we keep our vertex very simple, just the data. And we model these edges without the help of vertex or the node, independently. So there are different techniques. Okay, any of the techniques will work, but some techniques are better in certain situations than the other. So therefore, depending on your requirement, we can decide which technique we want to use. So we'll look at 3 of those techniques. The first one is use of adjacency matrix. Second one is using adjacency list. The third one is incident matrix. Any of these can be modeled and also implemented using code, Java or C or whatever. All 3 are implementable. But we don't have to do all 3. Usually we use one of these 3. Okay. Right. So let's take one by one. So these are super easy concepts. Adjacency matrix. Right. So adjacency matrix is, you put it into a matrix. You have learned matrix in your O-level maths. Okay. Matrices. So matrix is a 2-dimensional arrangement of data. Say these are my nodes A, B, C, D. This is not unidirectional graph. So therefore I have A, B, C, D in the horizontal way, and also I put it in the vertical other way, A, B, C, D. By default, let's assume they are all 0. Okay. By default, let's assume they are all 0. Then this is also 0. 0 is also 0. 0 is also 0. So 0 means there is no connection between these nodes. Okay. There is no connection. Now what we make is, those who are having connection, we may mark it as 1. For example, there is a connection between A and C. So therefore, A to C, I will mark it 1. A to B, A to D. Right? A to B, A to D, I will mark it as 1. So that is from A to other thing. So then we'll start with B. B to A, B to D. B to A, B to D, I will mark 1. Others will keep 0. Then C, only C to A. Then D, D to A and D to B. Right? So others are kept 0. So these are 0. And others are 1. Others are 1. And now we call it adjacency matrix. And this represent the graph. So graph is represented by adjacency matrix. And by looking at the adjacency matrix, we can build the graph. And you must be able to do both. Of course, that is not rocket science. That is super simple. Okay. And here we assume that it is bidirectional. So therefore, when you have A to C, there's C to A. So for example, when you have A to C, there is C to A. Okay. So because it's unidirectional or bidirectional graph. If it is a bidirectional graph, you can see that it is symmetric, right? Symmetric. If you draw this diagonal, it is symmetric. So this is there, 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 and this is there, this is there. You can see it is symmetric in this diagonal. So that is the case if it is unidirectional graph or bidirectional graph. But if it is not bidirectional graph, you may have this, but not this. That means you have A to B, but not B to A. That is something like this. Okay. So therefore, if it is unidirectional graph, it is symmetric matrix. If not, it is not a symmetric matrix. Okay. Right. I will draw a matrix. You have to draw the graph. Okay. Just a small exercise. Right. So this is my matrix. A, B, C, D, A, B, C, D. And this is directional graph, not an unidirectional graph. So therefore, this may not be symmetric. Okay. But some cases there can be A to B and B to A both. In some cases, it's only one direction. Okay. Right. So this is my data. 1, 0, 1, 0, 0. Sorry, this is 0. 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0. Right. Draw the directional graph for this adjacency matrix. Take 1 minute because 1 minute is enough. Assume it's a directed graph. Right. So it's super easy, right? It's not a big thing. Right. So let's draw it. From A, there's A to C. And this is now directed. I told you it's a directed. So then we have B to C and B to D. Let's say this is B, B to C, and maybe B to D. You can arrange it a little bit slightly different later if there are crossings. B to C, B to D. So then C to B, that is, this is both way, C to B, Then you have D to A. D to A. And this is your graph. Right? That is your graph. It's a directed graph. But in this way, it is both sides. That is, you can go from B to C as well as C to B. But here it's A to C, but not C to A. If C to A is there, this must be 1. Okay. Right, so that is how we model using adjacency matrix. It's super simple. Okay. So the next approach is use of adjacency list. And it is even easier. So you take the vertex and as a list, you write down what are the connected vertices. So A is connected to C, B, and D, or B, C, and D. B is connected to A and D. C is connected to A, and D is connected to A and B because it's bidirectional or unidirectional. That is called adjacency list. And again, when adjacency list is given, you must be able to draw the graph also, both way. Given a graph, write the list. Given the list, draw the graph. Okay. Right. So third approach is called use of incident matrix. That is also super easy. Right. Right. So there, what this is how you do. It's super easy. Say this is my graph, and assume it's unidirectional. So there are, say, how many vertices are there? A, B. Okay. Say A, B, C, D, E, F, G. So you just write those things. A, B, C, D. Remember, this is also part of it. It's not connected. That is fine. E, F, G. Okay. So then each edge is a column. Each edge is a column. So number of rows is same as number of nodes or vertices. Number of rows is same as number of vertices. Number of columns are same as number of edges. Now remember, adjacency matrix is a square matrix. Number of vertices is number of rows and also number of columns. But here, number of rows are number of vertices, number of columns are number of edges. So therefore, we have 1, 2, 3, 4, 5, 6, 7 rows. But we will have 1, 2, 3, 4, 5, 6, 7. In this case, 7 columns also. That is because we have same number of edges. Right. So now we have to mark each and every edge. You can see there's an edge between A and C. Okay, let's take this. You can mark it in any order. I will first take this edge that is going from A to C. So A is 1, C is 1, all the others are 0. That is AC edge. Then I have, if it is bidirectional, you have to mark CA edge as well. Right? CA edge as well, because it's bidirectional. Okay. Of course, this is bidirectional, right? Because there's no thing. So therefore, let's mark the CA edge as well. That is, of course, this is bidirectional anyway. So therefore, CA and AC is the same. So then let's go for AD. AD. You can go by any order. Order is not important. So then mark CF, C1, F1, all the others are 0. And likewise, then you can have FD, FG, B. And every column, so this is the incident matrix. Every column you have maximum of 2 ones. That is your edge. That is your edge. You can't have more than 2 ones. So for last column is basically B, E edge. That is this edge. Okay. But this can be used for unidirectional, because if it is directional, AC and AC is the same. Right? AC and CA is the same, right? So there's you can't distinguish between AC and CA. By looking at a column, you can't say whether it's AC or CA. So therefore, this approach works for unidirectional or bidirectional graphs. Okay. And this incident matrix can be used to extend few more concepts. Okay. Right. So we'll stop at this point because from this point we have to do the coding. So coding part we'll do next time and we can actually finish this topic next time. So we have to now model the vertices and edges, and then we'll look at how to do traversing, breadth first traversing, depth first traversing. We will be using a stack and cube. Okay. So we can do the coding for those things, but other things we don't do the coding because other than that, we have something called the very interesting problem called finding the shortest path. Okay. But we will look at how to do the shortest path as a technique, but we will not doing the how to do it, right? And so on. Okay. So we'll do some coding and then few more concepts, and then we will finish the graph. Then we have only do the search and sorting. Then your syllabus is over. Okay. We'll stop at this point, right? Thank you. And again, I gave you another, sorry, I want to do that one also. I gave you an exercise to your Google Classroom, WhatsApp group. I gave you a small exercise for you to draw the ER diagram. Okay, so I think about 3 students had given me the answers. I gave them the answer. I corrected their solutions. Actually, one student's answer was 100% my answer. Others 2 students answers actually that is from grade semester 3 students because I publish it for the final year student also. So this is for your final year project, because I know that when you go to the final year, the majority, they can't draw the ER diagram. That means they can't start their project. Unfortunate situation. If you can't draw your ER diagram, how can you start your project? Right? So they are also doing order processing systems, right? Saloon management systems, car rental systems. So they start, but they can't draw the ER diagram. That means you have not done your job properly in your database subjects, semester 2 database subject. So that is why I gave you ask you to draw the ER diagram, the analysis ER diagram, and then design ER diagram. Okay. So make sure you do it, right? So then later I will give you another one, but you have to do it by yourself. So today I will post the solution for this one, model solution. So then you can learn, those who attempted, they can learn something, right? So then I will give you another exercise like this, maybe little bit more complicated one. So this is super simple, but only one student gave me the exact answer. Other students, they were very close, but at least now they can understand what are the issues they had, practical issues you had when you draw the ER diagram. Because when you start doing real world things, all the practical things come into your mind. When you start coding, right? As long as you are living in a hypothetical conceptual world, you don't have any problem. The moment you get into the real world, you have thousands of problems. So I just want to put you into the real world as quickly as possible. Otherwise, when you go into the final year and start the project, you will feel like really, how do you call it? හරිම අසරණ හැඟීමක් දැනේ. අසරණ හැඟීමක් දැනේ. අනේ මට මේක කරගන්න බෑනේ කියලා. ඒ අසරණ හැඟීම දැනනවා ලබා ගන්නවට වැඩිය හොඳයි. ඊට පස්සේ ජොබ් වල පෝස්ටින් දැක්කම හැංගේවි නේද? ඔයාලට පෙනේ টොප් ජොබ්ස් වලට ගියාම අර ජොබ් එක මේ ජොබ් එක වලට හරි අසරණ හැංගීමක් දැනේ. අනේ මට එහෙම ඇප්ලයි කරන්න කන්ෆිඩන්ස් එකක් නැහැනේ. මට ඉන්ටර්විව් යන්න කන්ෆිඩන්ස් එකක් නැහැනේ. මට බයයිනේ. ඒක ඉතාලම අසරණ හැංගීමක්. හරි ඩිග්‍රියක් කරලා ඉවරලා එහෙම හැගෙනවා නම් ෆයිනල් ඉයර් ප්‍රොජෙක්ට් එක ලඟ වෙදී එහෙම හැගෙනවා නම් ජොබ් එකකට ඇප්ලයි කරන්න අසරණ හැංගීමක් දැනනවා නම් ඒගොල්ලෝ තමයි පාරවල් දිගේ ඊට පස්සේ දුවන්නේ නේද? රැකියා විරහිත උපාධාරීන් කියලා අපිට ඩිග්‍රී තියෙනවා කිය පෙන්වන්නේ නැහැ අසරණ හැංගීම. පෙන්වන්නේ අපි උගත්තු අපිට ජොබ් දෙන්න ඕන කියලා දුවන්නේ නේද? ඔකුන්ට ගහන්න ඕන ගාලි බවුසර් වලින්. හරි? ඒ අසරණයුන්ට. අසරණයෝ කියලා ඉතින් කරන්න දෙයක් නැහැ. ඒගොල්ලෝ ඉගෙන ගත්තේ නැහැ තමන්ගේ ඩිග්‍රී ඇතුලේ නේද? ඒකත් තමයි බලහත්කාරයෙන් රස්සායිල්ලන්නේ. So එහෙම නොවෙන්න නම් so you must be able to draw ER diagram, you must be able to develop a system, right? Start coding, start build the UI, right? So do these things, right? Only 3 students gave me the answers, right? Others I don't know whether you don't care. You know, අර වගේ එකකට බැඳිලා තමයි වෙන්නේ. හරි? Right. We stop at this point.